Here we want to work towards the big result that says that if D is a unique factorization domain, then D adjoin X, in other words, polynomials with coefficients in D is also a unique factorization domain. So this is a really important result. And it's going to require a lot of buildup, which I've outlined over here. And first of all, we have our assumptions. So let's say D is an integral domain and F is its field of fractions. So that's going to be an important step, is to push some of the work towards the field of fractions. Then next, if we've got a polynomial a sub n, x to the n, all the way down to a sub 0 in D adjoin x, then the content of P of x is said to be the GCD of all of those coefficients, so that's a definition. And then furthermore, P of x is primitive if the content equals 1, so that's another definition. And then we have these three lemmas which we're going to need. The first is called Gauss's lemma, and that says if that f of x and g of x are in D adjoin x and they're both primitive, then so is their product. So the product of two primitive polynomials is also primitive. Then next, the content of f of x times g of x is equal to the content of f of x times the content of g of x. So this function, if you will, that attaches a number, the content, to a polynomial is a multiplicative function, so that's what we're seeing here. Then finally we have this lemma, which essentially says that if you can factor a polynomial in the field of fractions, then you can also factor it in the integral domain. And so we write that in the following way. So if you've got P of x in D adjoin x, where P of x factors like f of x times g of x in f adjoin x, then there are polynomials which I'll call f hat and g hat inside of D adjoin x, where P of x equals f hat g hat. So what this says is if we've got a factorization in the field of fractions, then we've got a factorization using just coefficients in the integral domain. So we've actually seen this already with the rational numbers and the integers. This is just a generalization of that property. And then a very, very quick corollary to this is that P is irreducible in D adjoin x if and only if it's irreducible in F adjoin x. So that follows immediately from this lemma, and that's pretty easy to see. Okay, so let's get to proving. We'll start off with Gauss's lemma. So we want to do this by contradiction. So let's write that. So by way of contradiction, we want to assume that f of x and g of x in D adjoin x are both primitive, but f of x times g of x is not. Okay, good. So since f of x times g of x is not primitive, that means its content is not equal to 1. But if its content is not equal to 1, that means there's a prime that divides all of its coefficients. So let's go ahead and take P in D to be a prime such that P divides all coefficients of f times g. So let's write that like this. All coefficients of f of x times g of x. Now we know that f and g themselves are primitive. And what that tells us is that P does not divide all the coefficients of f of x or all the coefficients of g of x. So let's go ahead and write that down. So f of x, g of x, primitive, which tells us that P doesn't divide all of their coefficients. And that's an important distinction between primitive polynomials and non-primitive polynomials. Okay, so since it doesn't divide all of their coefficients, there is a minimal coefficient that is not divisible by P. So let's go ahead and bring those into existence. So let's suppose R is the smallest such that P does not divide AR, and S is the smallest such that P does not divide BS. And I should say here, where f of x equals an x to the m all the way down to a0, and g of x equals bn x to the n all the way down to b0. So that's the notation that we're using here. Now we'll use the fact that P divides all of the coefficients of f times g in order to get a contradiction. So let's go ahead and set C r plus s equal to the coefficient of x to the r plus s in f of x times g of x. So the formula for the product of two polynomials tells us that this coefficient is of the following form. So we have a sub r plus s, b0, plus all the way down to a sub 0, b r plus s. Something like that. But now, notice that we can rewrite this in the following way. So this is ar plus s times b0, all the way down to ar plus 1, bs minus 1, plus ar bs plus ar minus 1 bs plus 1, all the way up to a0 br plus s. Okay. Fantastic. Now, notice we know that P divides C of r plus s. So that's given because P divides all of the coefficients of f times g. Also, P divides this object. And we know that because s is the smallest that P does not divide b sub s, but everything in here has b sub something smaller than s. So we're good to go there. And similarly, P divides this thing right here for the same reason, but with bs exchanged for ar. But now, moving all the stuff around, notice that we can say that P divides cr plus s minus this big term minus this big term. But the difference of all of those tells us that P divides ar times bs. But what that tells us is that P divides AR or P divides BS, which is a contradiction. And that finishes the proof of this first lemma. Okay, now we're ready to look at the proof of this second lemma, which is a little bit shorter. So let's go ahead and set f of x equal to a times f hat of x, where a equals the content of f. And what that does is that makes f hat primitive. So we factored a GCD out of the polynomial, and I should say a GCD of all of the coefficients, but that leaves you with a group of coefficients which is kind of obviously relatively prime, but that's the same thing as saying this polynomial is primitive. Now we're going to do the same thing with g of x, so we're going to write that as b times g hat of x. And then we're going to say b is the content of g of x. And furthermore, g hat of x will be primitive for the same reason exactly. Great. But now notice we can write f of x times g of x as a times b times f prime of x times g prime of x. But we know from the last lemma that the product of two primitive polynomials is still primitive. So we know that this is primitive. But we've got a primitive polynomial times a coefficient, but that makes the content of f of x times g of x clearly equal to a times b, which is exactly equal to the content of f times the content of g. And so that finishes the proof of this lemma. And now we're ready to move on to the proof of this last lemma, which is maybe the most important for proving our eventual goal. Okay, so we're going to suppose that p of x is in d of x, and it factors like this in f of x. So in other words, suppose we've got p of x in d adjoin x. We're considering that as being injected into f adjoin x. And then we have p of x equals f of x times g of x. And I should say each of these, f of x and g of x, is in that field of fractions. Okay. So since it's in that field of fractions, the coefficients of f and g have so-called denominators. So that means that we can clear the denominators by multiplying by something in the integral domain. So let's take a and b in the integral domain so that a times f of x and b times g of x are in d adjoin x. So in other words, that like clears the fractions of the coefficients inside of the polynomials. So you can think of these as like the LCMs of the denominators of the coefficients if you want to do something like that. Okay, so now the next thing that we want to do is we want to find a hat and b hat in D so that we can write a times f of x equals a hat times f hat of x, where f hat of x is primitive. Okay, so if we've got something which is in D adjoin x, now from that we can factor out a greatest common factor from all of the coefficients to create a primitive polynomial, just like we did kind of in the last proof. And then we'll do the same thing for g of x. So we've got b of x times g of x is b hat times g hat of x. And here where we have g hat of x is primitive. Great. Okay, so now the next thing that we want to notice is we can take this a times f of x times b times g of x. Notice that's a times b times f times g, but that's equal to a times b times p of x. All of this is happening within D adjoin x, so that's interesting to know. But if we multiply down the right side of this equal sign, we get a hat, b hat, f hat of x times g hat of x. Okay, good. But now, since f hat and g hat are primitive, that tells us that we've got some sort of divisibility property between a, b, and a hat, b hat. In fact, we know that a, b divides a hat, b hat. Again, because f hat and g hat are primitive polynomials. Okay, good. But notice this tells us that we can write a hat, b hat as something c times a, b. That's just the definition of divisibility there. Now what I'll do is I'll take this equation right here and I'll rewrite it using this equation. So that's going to give us a, b times p of x equals a, b times c f hat of x, g hat of x. But then inside an integral domain we have cancellation. But since D is an integral domain, D adjoin x is an integral domain, so we definitely have cancellation. So we can cancel the a, b from both sides. And notice that gives us p of x equals c times f hat of x times g hat of x. So we have our factorization, which is all happening within D adjoin x. And furthermore, we know that the factorization involves polynomials of the same degree. So that's important to keep in mind as well. Okay, great. So we finished the proof of our last lemma. And now we're ready to prove our main result. So that says D is a UFD if and only if D adjoin X is a UFD. So actually this reverse direction we're not even going to do. It's super easy. So let's just talk through that in words. So if D adjoin X is a UFD, then all polynomials factor uniquely, including constant polynomials. But the constant polynomials are exactly the domain D itself. So we're good to go there. So all we need to do is go in this direction. So we'll have two things to prove here. The first is factorization into irreducibles. So let's make sure we prove that first. And then the next thing is to prove uniqueness of that factorization. But we've got to be able to factor it first of all before we can do anything. Okay, so let's go ahead and take P of x in D adjoin x, and we're going to view it inside of F adjoin x, where that's the field of fractions. Now the next thing that we know is that F adjoin x is a PID, which implies that it's already a UFD. It's in fact a Euclidean domain, which implies it's a PID, which implies that it's a UFD, but that's kind of neither here nor there. But what that tells us is that we can already factor this thing into f1 of x all the way up to f sub n of x with maybe f sub I of x in f adjoin x irreducible. Great. Now all we have to do is push this factorization, which is happening inside of f adjoin x, the field of fractions, into something d adjoin x, in other words, the integral domain. So we're going to do that by clearing the denominators in these, just like we did in the last case. So let's go ahead and take ai in d so that ai times fi of x is in d adjoin x. So that's going to be like n different numbers from our integral domain that take our polynomial, which is in the field of fractions, and clear the denominators to make it inside of the integral domain adjoin x. Okay, but now we can do the same kind of thing we did with the last proof, and that is, since this is inside d adjoin x, it is equal to something from the integral domain times a primitive polynomial. So again, we'll take bi in d such that ai fi of x equals bi gi of x, where the gi of x are primitive. So let's say this is in d adjoin x are all primitive. Okay, so now the next thing we want to notice is that these are irreducible by the corollary to this lemma. So notice they're irreducible inside of f adjoin x, which makes them irreducible inside of d adjoin x. So that's super important to notice as well. Okay, great. So now we're going to mimic what we did in the proof of this lemma. In other words, we're going to look at a1 all the way up to an times p of x. So I'm going to go ahead and rename this guy just plain old a. So we have a times p of x. So, but notice that that is exactly a1 f1 of x all the way up to an fn x. But we know each ai fi x is a bi gi x, so we can write that as b1 all the way up to bn g1 of x all the way up to gn of x. Now I'm going to do something similar. I'm going to take all of these and combine them together into a b. And then another thing I'm going to notice is that we know that this product over here is made up of primitive polynomials, because each of them are primitive, which makes their product primitive. Okay, so let's see what we've got. We've got a times p of x equals b times g1 of x all the way up to gn of x, where g1 of x all the way up to gn of x is primitive. Great. But since it's primitive, that means the GCD of all of the coefficients in this product is equal to 1, which means A has to divide B. So let's write that down. So A divides B. In other words, B equals AC for some C which is in the domain. But now we can take that and rewrite this as A P of x equals A times C times G1 of x all the way up to Gn of x. But next, we can use our cancellation, because we're in an integral domain, to cancel off A in both sides. Now we've got irreducible polynomials there, but this is just an element of the domain. But we know we have a unique factorization domain D, which allows us to factor this number into C1 up to Cm, G1 of x, all the way up to Gn of x. Okay, so let's reiterate what we have finished with. We have our polynomial is equal to a product of irreducibles from the UFD, which are irreducibles inside of the polynomial ring, times a product of irreducible polynomials. In other words, we factored our arbitrary polynomial into a product of irreducibles inside of the polynomial ring. Okay, so that finishes off the factorization part. And now we're ready to prove the uniqueness of this factorization. So let's go ahead and suppose we've got two factorizations, and then we'll prove that uniqueness. So let's say we have p of x equals a1 all the way up to am, and then f1 of x all the way up to fn of x. And then we have b1 all the way up to br, and then g1 of x all the way up to gs of x. So we factored this two different ways, one with m elements from the UFD, and then n polynomials, and then one with r elements from the UFD, and then s polynomials. So the next thing that we're going to view this all inside of f adjoint x, which is a PID implies it's a UFD from before. So that means if we're factoring inside f adjoint x, which is a UFD, we must have the same number of polynomials. In other words, n has to be equal to s. They're all associates to each other. So in other words, and we can rearrange so that gi of x equals ci over di times fi of x for ci and di inside of the integral domain. In other words, we can reorder all of these polynomials so that the ith polynomial g is an associate of the ith polynomial f. Okay, but from here we can quote unquote clear the denominator, and that's going to give us ci fi of x equals di gi of x, and that's happening all inside of d adjoint x, which is good because we don't want to spend all our time inside of f adjoint x, because what we're trying to prove, which is happening inside of the polynomial ring of the UFD. Now the next thing that we're going to use is the fact that up here we can choose each of these to be primitive. And we can do that by the proof of the factorization part. So we've chosen these to be primitive, which tells us that ci and di are associates. Because we know that the GCD of the coefficients here is 1, the GCD of the coefficients here is 1, which tells us the content of this side is ci, the content of this side is di, which tells us that ci and di have to be associates. In other words, they differ by a unit, so that means we can write di equals ui times ci, where ui is a unit. So that's the definition of being associates. Okay, so the next thing we can do is stick all of this information into our original equation, which tells us that a1 all the way up to am times c1 all the way up to cn times f1 of x all the way up to fn of x. So that's what happens to the left-hand side of this, is equal to b1 all the way up to br times, now we're going to replace g1 through gn in this case because we know that n is equal to s, with the fact that di and ui are units, and that allows us to write them all in terms of f of x. So in other words, we have u1 all the way up to un, and then c1 all the way up to cn, f1 of x all the way up to fnx. Okay, so we've got that. So now that's a big equation, but the lucky thing is that this is all happening within an integral domain. So recall that polynomial rings over an integral domain are also integral domains, which gives us cancellation. So we have this c1 through cn cancels this c1 through cn. This f1 through fn cancels this f1 of x through fn of x, which tells us that we have a1 all the way up to am equals b1 all the way up to br times u1 all the way up to un. But this is an equation that's happening all inside of D, which is the original UFD. And since we're inside the original UFD, we know immediately that m equals r. In other words, we have the same number of irreducibles here as we do here. And then furthermore, they are associates up to reordering. So let's go ahead and write that. R associates, and by they I mean the AIs and the BJs, up to reordering. And how do we know that? We know that's because all of that's happening within inside of D, which is a UFD to start with. Okay, so let's kind of reiterate what happened here. We started with P of X, which was inside of D adjoin X. We factored it two different ways. Using the fact that F adjoin X is a PID gave us some sort of uniqueness among the Fi and the D and the Gi. In other words, they are associates to each other. And then pulling the coefficients down to happening inside of the UFD itself showed us that these coefficients were associates to each other as well. So that finishes this proof, and that's a good place to stop this video.